Now I want to introduce something interesting here. Well, let's go think back to electric field. When we had an electric field, E, and we had a charge Q, and we moved the charge Q some distance in the electric field, we came up with an interesting sort of relationship. And that was the voltage here, or the electric potential, was minus the integral of E dot dx. And so this integral E dot dx turned out to be the electric potential. The electric potential, we know, is the electrical potential energy per charge. And so that idea of voltage or electric potential turned out to be an extremely useful concept for us. And so the question is, if integral E dot dx is useful, would integral B dot dx be useful? And that's a good question. Does integral B dot dx, is that really of any use to us? And so we start thinking about it, and we say, well, let's consider this integral B dot dx and see what does the integral B dot dx do for us. And so we look at it, we think about it, and we say, well, let's go ahead and try to actually do this. So what we're going to do is we're going to start with a simple case here, that we have a wire with current running down it. So if you put your eye at the end down here and look at it, then that means that we got the current, and the current is coming at you, and the magnetic field is going around in that fashion. If you put your eye down here and look at the end of it there, that means the current's going away from you, and the magnetic field is doing that. Okay, so what I want to do is, so if you look at it, that means that, again, that means the magnetic field is coming towards you here and then going away from you there. Okay, so what I want to do is imagine a loop following along with the magnetic field. So I'm going to follow along with the magnetic field. So I'm going to come out up here, in there, up here. So I'm going to do a loop, one complete loop. So let's figure this integral B dot dx. And I'm going to put a little circle there to indicate it's actually a closed integral. It's integral along a particular path through space. Now, since I'm going in the same direction, then it's just integral B dx. Since I'm constant distance from the wire, then the B comes out. So again, this is the same strategy that we normally do, is that we try to make our path such that the integral that was really complicated becomes a very simple integral. So magnetic field's constant since I'm always the same distance as the wire, so that means this is just going to be B times x. Well, what is x? X is going to be the distance around, so that's 2 pi r. What is B? B is the magnetic field of a wire. So the magnetic field of a wire, we know, is mu naught I over 2 pi r. So this integral B dot dx is going to be, it turns out to be equal to mu naught I over 2 pi r times 2 pi r. Well, integral B dot dx is just going to be mu naught I. Okay. Now, here's the interesting thing, and that is, we're going to call this Ampere's law. And we'll call it Ampere's law in just a second. We add one more interesting detail to it. If I got a wire right here, and let's say the current's coming at you, so the magnetic field is going around that way. If I have another wire right here, so that's going to be I1, I2, its magnetic field is like that. But if I were to do my loop like this, then what happens is that I'm increasing I'm going around this way, but on the other case here, as I'm going this way, then this magnetic field is changing as I go, okay? And so in fact, if I look at it from, very far away, okay, so very far away, if I have a loop like that, okay, then in some places it's positive, some places it's negative. So it basically, the integral cancels unless unless the current is in the middle. Now the other thing that is a little bit more difficult to show mathematically is that even if my current is there and I go off center here, magnetic field stronger here, weaker there, it still ends up being the same. So what we discover is kind of just like Gauss's law. Remember, Gauss's law said that the integral across the surface of E dot dA is going to be enclosed charge over epsilon naught. So that was Gauss's law. Now this integral B dot ds is going to be equal to mu naught times the enclosed current. So now it's just the enclosed current that's in there. Now that is really the statement of Ampere's law, that this integral B dot ds is simply equal to mu naught times the enclosed current in our little loop. Okay, that turns out to be very useful for figuring out magnetic fields in several different applications, just like Gauss's law was very useful for figuring out applications before. While I'm at it, we're going to introduce the idea of Gauss's law again in a little bit with magnetic fields. So we're going to introduce the idea in the next chapter of integral B dot dA. Okay, so remember, integral of E dot dA is a measure of the electric flux. And that was equal to enclosed charge over epsilon naught. This is going to be a measure of magnetic flux. It's going to be equal to the total magnetic charge over epsilon naught. Well, there is no, or not epsilon naught, but mu naught. There is no magnetic charge. There is no magnetic charge because you are always going to get dipoles, both plus and minus. And so that means that we are now across an enclosed surface. Magnetic flux, total magnetic flux is zero. That means just as much magnetic field goes in as goes out. And so that gives a little bit different feel of things. So we now have two equations for Gauss's law, one for magnetic flux, one for electric flux. We'll be using this later on. And then we have an equation called Ampere's law, which turns out to be a very critical sort of thing too. We'll see a little bit later in the semester. All we need is one more equation, and then we come up with a set of four equations that if you started with those four equations, you could have actually derived everything we've done this semester. Okay, so we'll get there later to these four fundamental equations.